In this lecture, we will learn about an overview of nanostructures and nanomaterials, because in the world of nanotechnology, it is very essential what that world comprises of. That means nothing but nanomaterials, and how do they can be blocked together to form certain pattern or certain structures, so that they can be utilized for an engineering application. So, we learn a lot much about science of materials at nanoscale, that is nanoscience of the nanomaterials, followed by constructing them into certain structure or utilizing a particular structure existent at that particular scale, and utilizing those concepts and building it for a much higher length scale bulk material or a component for actual or for a real life application. So, in this particular lecture, we will see overview of nanostructures and nanomaterials. So, just to start with, nanostructure is nothing but an entity, a geometrical entity with a distinct shape having nanoscale dimension. So, nanostructure, we are talking about certain entity, certain pattern which has a certain shape and certain size with the dimension, at least one of its dimension in the nanometer scale. Certain examples include carbon nanotubes, fullerene, carbon onions, nanofibers of zinc oxide, nanocrystals of diamond, certain nanoparticles of gold, and many other. So, there are many different types of materials. They can be a tubular shape as in carbon nanotube, they can be a ball shape or a soccer ball shape as in fullerene, carbon onions, some sort of rings, and the nanofibers of zinc oxide, nanoparticles which are again spherical. Again, this nanostructure terminology is not really new, it has been existent as in biology we have DNA double helix strands. So, this structure, it is consists of DNA, single strand is approximately 2.2 to 2.6 nanometer. It means that nanostructure have been existing for long. It is just that we now know of them, and we are able to see them, we are able to characterize them, and at the same time we are able to tap it for certain engineering application. Even the wall of the cell wall of bacteria also is couple of nanometers. So, again we can see the protein nanolayers in nacre is also to the order of around couple of nanometers. So, we can see that this nanostructure have been already existing in nature, and right now the overall idea is to be able to engineer them. So, we have to build them block by block and somehow engineer them for certain useful application, and the size remains again in the nanometer, and that nanometer scale can be constructed to form a microstructure and then a real bulk scale to utilize them as a engineering components. So, again we can see nanostructure is nothing but an entity, it is a geometrical entity which has a certain shape associated with it, with dimensions at least one length scale dimension in the nanometer regime. Certain examples include carbon nanotubes, fullerenes, carbon onions, zinc oxide, nanofibers or nanoparticles of gold. There are many others as well. So, they have certain distinct shape associated with them, and this nanostructure is not really new, it has been already existing in nature, like certain DNA double helix structure or protein nanolayers in nacre, and even apatite crystals which are present in our bone. So, there are multiple number of examples which already have been existing in nature. Before we know about learn about nanomaterials, it becomes essential to realize the certain terms or certain terminology which are essential in learning nanomaterials. As we all know that nano is nothing but a prefix of 10 power minus 9, and once we associate the unit of length to it, it becomes 10 power minus 9 meters. So, it is also called nanometer. But there are certain entities which we need to learn about, something like nanoparticle. So, nanoparticle is nothing but a particle which has a size in the range of 1 to 100 nanometer, and it can act as an independent entity. It can always agglomerate and form much bigger units, and the individual entity will be called nanoparticle, but it has the capability of existing on its own. So, nanoparticle is a particle with the size in the range of 1 to 100 nanometer. About nanocrystal, nanocrystal is a freestanding monocrystalline nanomaterial. So, we can see nanocrystal is nothing but a freestanding monocrystalline nanomaterial, and which has at least one dimension in the scale of 1 to 100 nanometer. So, we can see nanoparticle. So, nanocrystal can be a nanoparticle as well. Then we talk about nanophases. Nanophase can be either crystalline, quasi-crystalline or amorphous. It is not only phase, it can also be associated with a property, such as we can talk about magnetic, or any particular domain, magnetic domain. So, we can always associate phase which is not only a structure like crystalline, quasi-crystalline or amorphous, it can also be a property such as magnetic or electric domains which can exist in a material. So, that is nano phase. So, each material can have multiple number of phases, and if one of the phases has a unit of couple of nanometers, 1 to 100 nanometer, we call it nano phase. It can again be isolation of certain particles which are either crystalline, quasi-crystalline or amorphous. So, again we will call them nano phase. Then we come to nano composite. Nano composite is a composite of two or more materials where at least one of them is in a nano phase. So, once we are talking about nano composite, at least one of the phases is nano. It means that that particular phase what we are talking about is either crystalline, quasi-crystalline, amorphous, or it has certain property associated with that, and it is existing in a mixture of some other matrix, or it can have two multiple nano phase matrices. So, in that case we call them nano composite. Then nanopores. It is a porosity which is a size range within of couple of few nanometers, 1 to 100 nanometer. So, it is not only phase or any freestanding structure or a crystal, it can also have certain pores which are again nano in size, and these can also impart certain very nice properties. So, this can be related to the structural colors which arise as in peacock feather. So, we can see nano terminology, it can exist as a nanoparticle. So, it is an independent unit entity which has size range of 1 to 100 nanometer. It can be a nanocrystal where we have a freestanding monocrystalline material with at least one dimension in the scale of 1 to 100 nanometer. And the nano phase, it can be either a structure or a property associated with a particular entity that is existing, that we call as nano phase. Now, nano composite comprises any one of the nano phase being existent in a composite material, and there can also be pores which are size within 1 to 100 nanometer, to them we call them nanopores. There are certain nano terminology which are associated with the nanomaterials. So, now coming to the structure, we can see the structure at various length scale. If we are talking about individual atom, so we know there is a nucleus associated with that, and there is a electron cloud around that, and now they keep vibrating at certain temperature, they keep vibrating around a certain region. So, that is what we call at atomic scale. We have atom, or many of the certain atoms can combine by certain bonds, and then they can link to each other. So, this we call either as atomic bonding, or it can also be individual atoms. So, we can see that either these are individual atoms, or there is some sort of bonding which is occurring, which is existing between the two to create. So, it can also have certain molecules like in H2O. So, we can see either they are either individual atoms, or these can also be ions which are existing. It can also have some sort of bonding at that particular scale, and it can be even molecules such as H2O. So, here we are talking about couple of range of approximately 1 angstrom or so. So, that is nothing but the atomic level. So, around 1 angstrom to 10 tens of angstroms, that is the level scale which we are talking about. Then once we come to a unit cell, now it comprises many more number of atoms. So, in this case, now we start seeing some regularity. So, we can see a unit cell, it comprises couple of atoms at different locations. So, it is being defined by either your the lattice now starts comprising certain motifs or certain bases to call it a crystal or unit cell. So, from lattice we add motif, and then what we get is some sort of a crystal, and that crystal is defined in terms of unit cell. So, we have gone from atomic level, which was couple of angstroms, to less than a nanometer, couple of nanometer as well. Then we have come to unit cell, where we are talking about couple of angstroms as well, and it can again extend to couple of tens of angstroms. So, again we can see from an atomic level we are going to a unit cell level, and now these many unit cells, once they are solidifying, once we start solidifying a material, it can start orienting in different directions. So, there are multiple number of unit cells which are oriented in very different manner. So, we get certain nucleating points and then it starts developing an orientation and then we see a microstructure develop. So, these now start forming certain grains. So, we can see, so this is orientation 1 and this is orientation 2. So, now we can see this unit cells, there are multiple number of unit cells, now they combine and then they provide a structure, but now we are talking length scales in the order of couple of micrometers. So, we have gone from couple of angstroms to maybe say tens of angstroms and then now we have come to a length scale of microstructure. So, something between, when this particular microstructure, it can vary from couple of nanometers to couple of micrometers. So, once we are talking about size range of couple of nanometers, we are working in the range of 10 power minus 9 meters, that is nothing but structure of or nanostructure, and we can observe that structure via say transmission electron microscopy, scanning electron microscopy or various other methods. But now this microstructure, though we call it microstructure, it can also be utilized for studying something at nanoscale, then it becomes a nanostructure. But this nanostructure, it is observation of that structure, it is not really a existing nanostructures. These are contrary terms. So, one thing is observing nano, that is nanoscopy, or seeing the nano material or a pattern, that is called a nanostructure. So, anything which is a pattern, a regular pattern, that is a nanostructure, but observing it at that scale we call it nanoscopy, but the regular terminology for using it is microscopy. So, anything micron or less we observe them using microscopy. So, we can see here from atomic level we have now gone to the unit cell level, and from unit cell level now we have come to the microstructure. Now, this microstructure can be developed via certain patterns and then we can develop a certain component which we require for engineering application. So, we can see this material will be now composed of multiple number of grains. This can be either micro grains or it can be again nano grains, and then we can make it certain useful unit. So, we can develop a more complex units or components by utilizing this particular material. So, now this one becomes a representative part of any particular component. So, we have component 1, component 2 and component 3 and other various other components to draw a engineering device or a particular structure. So, we can see we are going from atomic scale where we have atoms, 1 or 2 levels of atoms or molecules which are existing. Then these atoms they combine either in a regular fashion to form a crystal, or they can again be amorphous. So, once they are forming the crystalline structure, we can always identify them using certain unit cells. Now, these go up and they tend to form something called microstructure. It can be a nanostructure or it can be a microstructure. We observe them using microscopy technique. And now, once we have this particular material, once we have engineered it, we can go and form much more complicated structure as a component, which is a bulk entity, and we are talking about couple of centimeter to meter scale or even more. So, this is how the overall structure or the length scale is being now distributed. So, we see structures at various length scale going from atomic to again tens of angstrom, then couple of nanometer to couple of micrometer, and then going to centimeter or a meter scale. So, that is how we can see the structure at different length scales. So, the importance of microstructure is the way the orientation of these particular unit cells is occurring, that gives rise to properties which are either different or they are similar. If we can align everything along one direction, we can have very different properties along this direction, and we can have very different properties maybe say at certain angle of this one. If we tend to have very random orientation of all of these particular grains, what we can get is a average along all the side will be same, whether we take any direction the average will be same. So, now what we get is a isotropic property. It is no more anisotropic, it becomes isotropic in nature. So, that is the overall deal with the microstructure, and once we get an isotropic property at the bulk scale, we can utilize them as a component which has a similar properties in the all the directions. So, that is the essential, or that is the importance of learning about length scales. So, coming to the validation of length scale. So, as we talked, we have either atoms, ions, or it can be even molecules which tend to go and form certain phases. Phase, it can be defined either as a structure or a property. So, many phases they come together and they tend to form microstructure. So, once we have atoms, they go on to form certain molecules or even molecules or ions, they now tend to form certain phases. So, we can now see one phase, second phase, it can be multiple number of phases. So, we can see phase 1 and then, so we can see different phase 1, this is phase 1, this one is phase 2. Now, these are forming nothing but a microstructure. So, many phases they come together to form a microstructure, and now these many of these microstructures, it can be one type of microstructure, second type of microstructure. Now, we can see that many microstructures, now they comprise the material. So, we see in this case we have phase 1, phase 2. So, many phases they go and form microstructure, and this can be one type of microstructure. It can be stitched with many different type of microstructure. It can also have nanoporosity somewhere. It might have some bulk segregation as well somewhere. So, we can see it can develop a very complicated structure at micrometer length scale, and now these go on to form materials, because we can have not only one material, we can have many more number of type of material which can form the bulk component or the bulk material. So, we can have say combination of CuAl. The manner in which Cu and Al will come together, they can also form certain precipitates. So, we can see the precipitation generation as well in the structure. So, in this case we can see the many material, many microstructures they go into form material, and now many material they can either form directly the component, or we can also form something called hybrids. Hybrids means we can have multiple layers and multiple properties which can come together to form a final component. So, again we can see this traverse from atomic scale to a bulk scale. So, we go from atoms or molecules which go on to form phases. These many multiple number of phases they go on to form microstructure. Many microstructures they are pertinent to certain material, and this material depending on how do we heat treat them, how do we process them, how do we apply certain environment, the properties can come out very differently. So, for even for steel, the way we temper them, the way we heat treat them, the way we process them, the way we do some mechanical treatment to them, the properties will come out very differently. So, we can have multiple number of materials. Now, they can be either layered, they can be formed hybrids, they can be now gradiently promoted to form certain components which can be again engineering for certain engineering application. So, we can see how the complexity of component arises from the basic unit, that is nothing but the fundamental building block, that is atom. An atom, it has a unique identity, and how its pattern can be changed at microstructural level. So, same atom how it can be arranged in a different manner to form different microstructures. So, depending on the thermal and kinetic profile of it, we can alter the microstructure of the material. So, that is now is the main cause of affecting the overall properties of the component, and that is what we can see that by incorporating either nanomaterials or by incorporating nanostructures, and by engineering those nanostructures we can exactly outlay the requirements which are required for the engineering design, and then we can incorporate them to form certain components which are lighter, which are much more stiffer, much more corrosion resistant, and much more efficient in terms of fuel utilization for the final application. So, we can see the development of structures, how it occurs from atomic to a bulk scale. Coming to the atomic level, we can see that generally atom will have a lattice point, and now it will start vibrating because of thermal fluctuations. It will have a mean position. So, atoms are constantly vibrating at temperature which is greater than 0 Kelvin. So, atom is ideally should be here, but it is not traversing everywhere else. So, we can see the order is only in the average sense, and the perfect order, it means the atom sitting exactly at one point and nowhere else, that is totally missing out at atomic level. So, we can see atoms are constantly moving at temperatures about 0 Kelvin because of thermal vibrations, and we get average sense of order. So, there is no perfect order which is available at the atomic level. So, that tells that there has to be some anisotropy associated with this one, because there is no order as such. Now, coming to a unit cell. So, many atoms they come together and they go on to form a repeating unit which is termed as unit cell for a particular crystal. So, we can see in this particular case we have a FCC unit cell. So, we have face centered cubic lattice in which we have atoms sitting out there. So, a unit cell is a level where we can now start seeing the atomic arrangement. So, because of certain pattern in which we are able to associate the atoms, now it becomes much more evident, and now there is something called a structure. So, now we are developing a crystal structure. So, from unit cell we had no order as such. At the level of unit cell we start seeing some order, where we can see the arrangement of atoms which become localized to certain locations of the lattice points. In this case it is a FCC lattice, and that becomes evident at this particular unit cell scale. So, in this case what we are seeing the development of a crystal structure that is being defined by a unit cell. So, what happens at the next scale is it is a microstructure, it is also called a nanostructure. So, in this case what is happening? In this case now we have nearly perfect order. Why? Because the scale of atomic vibrations which was existing in the even in unit cell, even in the atomic at the atomic level, it is now very negligible, because now we can see that our atomic vibrations are very small when compared to the length scale of 1 grain. So, once we are talking about 1 grain, the lattice vibrations are negligible. So, we can see negligible lattice vibrations. Though there can be presence of some defects such as vacancies or dislocations or Frankel defects or a Schottky defect or many other. So, we can see there can be vacancies, dislocations. These are certain imperfections which are available in a single grain. But what happens now? Material is now anisotropic within a single grain, because now we get a different properties like elastic stiffnesses along E11, E12, E44, they are very different. So, what can happen? That the material is anisotropic because now we have different elastic moduli, elastic stiffnesses along different planes or different perspectives. So, we can see that the material becomes now anisotropic, it has certain directionality. So, it might have much better properties say in this direction and maybe say in longitudinal direction than in comparison to that of a transverse direction. So, we can see the material is now anisotropic at a single grain level. So, we can see the most of the properties, it might have certain domains, it might have directionality in terms of magnetic domains as well. So, we can see the property is varying. For a single grain the properties are much higher or lower in certain direction. So, that makes the material anisotropic, but for a single grain. But the crystal might be just isotropic with respect to some other properties. It might have domains in this particular direction, but on an average a crystal might have certain magnetic domains which are aligned like this, all aligned maybe say in parallel to like this. They are aligned all parallel directing upwards. So, it has now certain magnetism along this direction, but the properties such as stiffness might be same in all the 3 directions. So, we can see E1, E2 and E3 might be just similar or same in all the direction, because these atoms are behaving in a similar manner. So, though they might have some domain, magnetic domain along this direction, a net domain, magnetic domain along vertically up direction, it might have similar stiffness along all the 3 directions. So, that makes the material anisotropic with respect to certain property, but might remain isotropic for other properties. But now, when coming to the bulk structure, we can see many such grains they can combine and they can form a bulk structure, and assuming that the grains are randomly oriented, what we can get, though we might have some disturbances or some differences in terms of some terms in terms of elastic moduli. Say E1 was much greater than E2 compared to E2, and E2 was again say higher than E3. So, we get some directionality in terms of the moduli. So, we might see that our x direction, z direction and y direction. So, maybe Ex was pretty high along one direction. So, now what we can see, the grains are now randomly distributed. So, what happens that and on an average there are multiple number of grains, there are millions of grains which are available in a particular bulk structure. So, on averaging, what we can get, that the elastic moduli and the material in terms of other properties becomes isotropic. So, that is the beauty of this particular part. So, we saw that at atomic scale, at level of unit cell scale, microstructure, and then at bulk, we are seeing much more isotropic property. We are seeing isotropic property even at unit scale. At microstructure, it might become anisotropic, and again in atomic there is no perfect order. So, it means again there was some anisotropy. So, we can see at atomic scale we had some orientation because of thermal fluctuation. So, it was not showing a perfect order. So, it means it has some preference to certain direction, makes it anisotropic. At unit cell, it can have anisotropy, but it might also have isotropy once we consider certain property. So, it might eventually come out that the unit cell has certain isotropy. At microstructure, we can see some orientation within a particular single grain. So, it might be anisotropic. When coming to bulk, when we have a random distribution, the material can again become isotropic. So, we can see the up down of the isotropy associated because of the different length scale, and we can control much of the structure at this particular length scale. By once we are able to control the material, we can alter the properties of the bulk structure. So, we should be able to control something once we have a nice understanding of how the structure is developing and how that particular property is associated with the orientation of that unit cell. We should be able to control the microstructure. So, if you know if all the magnetic domains are getting aligned, say along 100 direction, and there are 3 equivalent 100 directions. So, we also need a direction to it. So, if 100 is getting aligned to a higher extent, so if you can see 100, 100, so if we can somehow align all those planes together, we can get an additive effect along this particular direction. So, we can see it can be 100, this one can be 001 and this can be 010. So, if we want to get an additive property, we might want to align the grains along this side by controlling the solidification or by applying certain epitaxial film on which we can start growing the material along that particular direction, and now what we can get is a net magnetic domain along this 100 direction, and that thing can be controlled. So, we can enhance the material properties by controlling something at that scale, and that will yield a better engineering property via application of understanding the material at nano length scale. So, it is also like building block by block. We must have played in our childhood with certain building blocks, we call them Legos. So, we have a certain block and then we go on to forming certain structures, and then so from single blocks we can keep building up until we get a complete structure, and then so we started from a single block and now we are able to construct a entire component from it. So, we start with an atom, we go on to the length scale of a microstructure, a unit cell first. So, we choose a material which will align in a certain pattern. So, we get now multiple number of unit cells or a crystal set of crystals. Now, these crystals, the way they grow, they can go on to form microstructure. So, we can see a certain alignment of grain. What we get now is a microstructure. Once we are able to control the microstructure, we can have either a patterned layers, we can have a graded structure as well. So, the property will keep varying from top to bottom. So, in this case we can also see that we can utilize something called thermal barrier coatings. So, if we can, one material can sustain very high temperature, that is nothing but ceramic. So, we can have a ceramic layer, then we have a bond layer, and this is the base material which is now taking the maximum load. This is nothing but a metallic base material, it can be a super alloy. So, we can see that now this structure can take much more load at even high temperatures, because now we have a barrier of thermal coating. So, what we can see, this is a load bearing component. So, it is bearing the load. This one serves as an interface, and this takes most of the thermal load. So, now this base material is protected from the environment for oxidation or even for thermal load by this ceramic layer, because ceramics can take very high loads, and it has an interface to bind the ceramic layer with the metal, and then this metal, or it can be a super alloy, which can take the entire load for running the turbine at very high temperatures. So, we can see that we can start from very small layer of atoms, we develop them into crystals, develop the microstructure, build them into certain layers, it can be certain hybrids as well, and now we can play with the microstructure, and then we can even develop something called graded components. So, we can have varying properties at different depth of that particular component or material. So, that is how we can engineer by developing block by block of that particular entity as a structural or engineering marvel. Again, coming to the nanostructures. So, now we learnt a little bit about nanomaterials. So, seeing the nanostructure, this is nothing but a pattern geometrical, it has certain geometrical pattern associated with that. So, we can see in fullerene we have it is also called C60 molecule. So, it has multiple number of pentagons and hexagons to give it that shape. So, it looks more like a soccer ball. So, we can see here it has certain hexagons, this is a hexagon, this is a pentagon. So, which gives it a more of a soccer ball shape. It is also called Buckminster fullerene. Buckminster fullerene. So, that is what we can see out here. So, it has a set of hexagons and pentagons that eventually go on to forming this structure. So, we can see these hexagons are now being supported by a pentagon that is utilized, that basically provides the turning to this particular hexagon. So, hexagons are more like single layer, this thing are more like they have a sp two type of a bonding, and then these go on eventually to form a fullerene or a ball shaped structure, and this is couple of nanometer in size. Now, we can also have something called nanocrystals. So, we can have small crystals which are of the order of couple of nanometers. So, we can have say diamond nanocrystals. These are freestanding entities which can exist as a monocrystalline unit. So, we can see that nanocrystal, they have couple of dimensions of couple of nanometers along any one of the length scale, and we can also see, we can also have something called nanorods. So, in this nanocrystals they can have shape, any shape. So, the way they grow is depending on their basic unit. So, if it is a tetragonal shape, it might develop as a tetrahedral shape. So, that can be associated with the unit cell. So, unit cell is hexagonal in nature, that is how it will start growing. Nanorods, it is some unit, it has a rod shape, it can have a cross section of a circle, and it can even have a cross section of a hexagon, but these are filled units which are nothing but rods. So, we can again have zinc oxide rods, or maybe some other type of rod which can be even circular, it can be circular in the cross section, it can be cube type of it can even have a cube shape of a cross section. So, we can have either a cube type or a square type, it might have a square cross section, it can have a circular cross section, it can even a hexagonal cross section. So, these entities are existing when this dimension is nothing but in nanometer length scale. So, we can see the two of its units, nanorods means two of the units vertical, two directions along the vertical, the length might be couple of micrometer or more or less, but the other two entities are in the length scale of nanometers. In nanocrystal, we have entire dimensionality in nanometers. In nanorods, we can have dimensionality of nanometer along two of those dimensions, and the third dimension can be even longer. And in fullerene also we have all the three directions in couple of nanometers. So, that is how we can see fullerenes, nanocrystals and nanorods, how we can define them using this terminology nanocrystal. These are crystals, monocrystalline crystals which can exist in entirety, and then we can also have nanorods which have dimension of couple of micrometer along longitudinal, whereas only nanometers in case of the other two directions. So, the definition of nanostructures can even extend to some different type of patterns. It can be nanotubes, in which case like in case we can have boron nitride nanotubes or carbon nanotubes. In this case, a kind of a sheet, once it is rolled to form an entity, something which is a hollow tubular nature. So, we can see it has certain thickness, and that now has been rolled to form a certain tubular shape. It is no more a rod, it is no more a rod, it has some hollow structure, and this diameter of this particular tube is in the order of couple of nanometers, whereas the length can vary from couple of nanometers to couple of micrometers. So, we can see a single sheet once it is kind of rolled. So, if you can roll this particular sheet and join the ends, it can form a tubular structure. It can be made up of boron nitride or carbon nanotubes, or carbon to form boron nitride nanotubes or carbon nanotubes, and then it has a certain hollow structure. So, that is the reason we get the terminology of tube. So, that is again a nanostructure. The importance of this nanotubes is it can provide enhanced, it has very high modulus in the order of around 1 terapascal, very high bending strength or fracture strength. It can even bend without breaking. So, it can bend to very large extents even without breaking. So, we can see that it can bend to a very large extent. Once we start bending the carbon nanotubes, it can bend to a very large extent. And so, we can see that tubes are nothing but a hollow structure. Nanotubes, when the diameter of these tubes is around couple of nanometers, then we call them nanotubes. It can also form something called nanoflower. In this case, in case of nanoflower, we have some nucleating point, and from that we can see many different structures which can originate. So, it can form a rod like structure, it can also form dendritic structure. So, it looks more like a flower. So, whether it is either a kind of a rod shape which has a dimension of around couple of nanometer, being a very flowery kind of a structure. So, we can see, or even it can be many more, or it can vary depending on the dendrites which originate. So, we can see it appears more like a flower. So, when these dendrites, the thickness of these dendrites are approximately couple of nanometer. So, we can see that structure. It can also have rods. So, we can have a rod shape, it can have maybe a dendritic structure, or it can have a very different circular or petal shape. So, it can see many different morphologies which can originate in nanostructure. It can also be nanospring, like in case of zinc oxide, we can always provide a certain turn to it. So, we can see that this structure can develop more like a spring. We can control the pitch, we can control the turns, we can control the torsionality of this one. So, we can see this thickness also can be controlled. So, we can make even thicker. So, we can make it even thicker or maybe thinner, and then again this dimension is an order of couple of nanometer, and these are called more like springs. So, we can compress them or we can expand them, they can be made thicker and even we can have much more coiling of them can also be attained. They look more like the wires we used to have in the telephone line. So, these are nothing but springs that have a nano dimensionality associated with them. Even this dimension, the overall radius can also be approximately couple of nanometer for those nano springs. Now, coming to the quantum dots, we can also lay out certain heavy atoms using some probe tips. We can lay out individual atoms in the location we want them to form certain pattern. So, this provides a flexibility of taking atom by atom and placing it exactly where we want. Where required. So, we can take this individual atom, pick it up and then place it on a particular chip. So, now we can make very nice chip exactly where we want to put the atoms, and then we can make certain transistors, resistors, capacitors on a small chip, and that is how we can enhance the density of this particular circuits and improve the performance of a computer. So, we can see there are multiple number of structures. It can be Fullerene structure, it can be nanorod structure, it can be nanotube structure, nanoflowers, nanosprings, quantum dots. So, we can see a variety of such structures which emerge, and it can, right now we are talking only about certain structures which are solid. We can also talk about structure of pores, how we can organize the pores in a particular matter and then we can arrange it to get a different pattern. So, this is how we are defining nanostructures. Going to the next level, we can also arrange different patterns of those nanostructures. So, we can see a polycrystal with nano sized grains. So, we can see out here, then when we have a polycrystal, so either we can utilize the two faces, like in this case we have two faces. So, one face is the bigger one, so which is comprising maybe say around 60-70%, maybe more than 70%. So, that in this case it is the blue, and second face can be black. So, we have black face and then we have a blue face out here, and one of the entities can be nano in nature. Either we can make this second face, the black face, nano, and then we can disperse it out here, and also what we can do is we can also make this blue matrix also nanocrystalline. So, we can make the size of this particular grain only couple of nanometers. So, it is up to us how we can play along and then control the structure in which the way it is generating to control the final properties. In this case, what is one more uniqueness to it is that the black face is forming a continuous network along the grain boundary. So, all the grain boundaries are now enriched in the black face. So, that is again one way in which we can disperse the phase 2 in a phase 1. In the second case, what we can do is, so in phase 1 we are having a continuous network, and case 2 what we can have a acicular or a needle like shape of this second phase. So, in this the same again we have the black phase as the second phase, but in this case we have needles, and needles again can have a dimension of couple of nanometer diameter. The length can vary depending on the requirement or the manner in which the microstructure is getting generated. So, now this structure can have very high stress concentration at its edges or its tips. So, this structure might be deleterious for certain properties, but it might turn out to be very hard. So, we can so depending on the requirement we can alter this material and we can utilize the properties. Now, we can see a third case when we have the similar volume content, but now as a sphere. So, we have rounded particles. So, we avoid the stress concentration, and then we can now have rounded particles dispersed in a matrix. So, either this matrix be nanocrystalline, and even this rounded particles can be made nanocrystalline. So, in this case we can now see that the stress concentration along the edges is not as much as it would have been in the needle shape. So, we can enhance the ductility of the material, and this structure can be predominant say as in a nodular cast iron. Further, if we want to disperse these nodules, we can have them as very fine distribution of these rounded particles. So, we can see these rounded particles, they are no more available as a agglomerate, but now they are dispersed throughout the matrix in a much more uniform fashion. We can still go on and we can still reduce the size of this particular nodule or rounded particles, and we can make it much more finer later on. So, we can see this again, the way we can distribute the second phase particle can have very predominant effect on the properties of the material. In rounded particles, we may not get much enhancement in terms of its tensile strength or yield strength, whereas we can get much better ductility when compared to that of a acicular particle. And once we enhance the distribution, we can make the particles more and more fine. We can also attain enhanced toughening, enhanced strengthening, enhanced ductility, just because we will find many more number of these particular precipitates or those particles which can hinder the grain boundary movement, or they can provide as a obstacle to the movement of certain slipping phenomena, and they can enhance the overall strength. Also the toughness can also be enhanced because of these smaller particles. So, we can see the polycrystal with a nano size grain can also have variety of properties depending on the distribution and the size of the second phase particle, as well as also depends on the content of the matrix as well. So, we can see that engineering at nanoscale is a function of particle size, shape and distribution. If the particle is sitting at the grain boundary, if it is brittle, then it will make the entire structure highly brittle. If it is available as a acicular particle, it might induce certain stress concentration, again it might not be that much good to absorb certain shock. Once it is made as a nodule, then it can give out to much more enhanced ductility. If we can further improve the distribution, we can enhance the fracture toughness, we can increase the strength of the material while maintaining the or increasing the ductility of the material. So, that is what is the overall deal with the distribution of these nano sized entities in a particular matrix. Again, certain structures have been already existing in nature, like in case of missile, we can have a sphere of hydrophobic heads. So, we can see the heads which are coming in, joining together as a cluster, and then its tails which are hydrophilic in nature, they are in the. So, we can have a water. So, we can see these are hydrophilic tails, and it is they are clustering together hydrophobic heads. There is some maybe a water. So, we can see this is nothing but a missile structure which is existing. So, the central cluster is nothing but a hydrophobic head, whereas the tails are hydrophilic, which are dangling out of this particular globular structure, and this structure can again be nanometer in diameter. So, that is what it is giving rise to a nanostructure. And also we know that the DNA strands, the double helix type of a strand of DNA, it also has a nano dimensionality. It is a long repeating unit of nucleotides. It has a radius of around 1 to 3 nanometer. It is a pitch of around couple of 3.4 nanometers, and in this case we also know that we have 4 nucleic acids which are adenine, thymine, guanine and cytosine, and this always go and combine AT and GC, they tend to combine with each other, and if you can somehow separate one of these particular strands, we can get exact copy of what the other chain would have been like. So, this is chain 1, this is chain 2. So, once we can peel off the chain 2 and once we can somehow exactly identify what those nucleic acids are, and then we can always come back and we can identify what the chain 1 might have looked like, because our A and T, they always combine together, and G and C, the adenine, thymine, guanine and cytosine, how they combine together, and these entities are again nano in terms of their radius and also in terms of their pitch. That tells these structures have already been existing in nature as well. So, finally, how we can classify those nanostructures is, so we can define them in terms of their nano size dimensions. So, number of bulk dimension and number of nano size dimension. So, these are kind of contrary. So, we have total of 3 dimensions. So, we have, so what we can see, the number of nano size dimension and number of bulk dimension, they add to 3. So, if any entity which is nano in all the 3 directions. So, we have small very fine crystals which have the length, breadth as well as height, or if it is a particle, its diameter of the sphere, everything is nano in nature. So, there are certain examples are nano crystal of diamond, nano crystal of gold, or even quantum dots. So, these are individual atoms which are being placed together, and these are called nano entities. And the bulk dimension, it means anything which is much more than 100 nanometers in one of the dimensionality, that is 0. So, it appears more like a nanosphere or a nano crystal. If we have nano dimension only in 2 directions, like in case of wires or rods, we have the diameter approximately couple of nanometer, whereas the length can vary to couple of much more than nanometer. So, we have examples of nano wires, nano rods, nano tubes. Examples are carbon nanotubes, zinc oxide rods, or so on. So, in this case we can see the bulk dimension, it means the length has certain visuality to it, it is bulk. So, we can see the length can be couple of microns, that is the reason we have one dimensionality in bulk, whereas 2 other, that is the height and the width of it, it is nano in nature. Then we can have something called nano layers or nano films. In this case we only have the thickness, whereas the other 2 dimensions, the length and the width, they both are much more than nanometer. It is only the thickness which is a dimension of couple of nanometer. These form nano layers or nano films. Certain examples are epitaxial layer of say silicon germanium on silicon substrate. So, once we talk about thin films, these are nothing but nano layers or nano films, which is a dimensionality in the nano regime of 1. So, the bulk dimensionality will be 2. Because they have to be coated on a very large surface, as high as say this monitor or this particular screen. So, we can have 2 length scales which are quite big, much more than 100 nanometer, whereas only the thickness part is couple of nanometer. So, it comes under the category of nano layers. Then we have a third category when none of the dimension is in the order of nanometer range. So, then we have dimensionality of 0, whereas all the 3 directions, they are width, height and thickness, they all are much more than 100 nanometer. So, they become bulk scale. Example is bulk single crystal of silicon. So, we can see how the dimensionality is varying. So, nano dimension when it is 3, it is called nanoparticle. Dimensionality is 2, it is called nano wire, nano rod, nano tube. When nano dimensionality is 1, we call them as nano films or nano layers. When the dimensionality is 0, it has nothing nano in it, it is nothing but a bulk entity. That is how we can see how we can classify this all these structures. So, if one dimension is nano, we call it nano layer, 2 dimensions are in nano, we call them nano wires, nano rods, nano tubes. When all the 3 are nano, we call them nanoparticles or nano crystals. So, in summary, once we talk about nanostructures, we have to traverse along the length scales. So, we can see what is nanomaterials. We also need to define how the structure is developing. It can be tubular, rod shape, flower type, even it can be soccer ball like for fullerene. So, we need to also identify what is happening at the nanostructure, how we are able to define the nanomaterial and evolve them at different length scales, and how the dispersion is decides the overall variation of the properties. Like if the second phase is along the grain boundaries, if it is present as a acicular phase, if it is present as a globular phase, or if the dispersion is occurring, how properties can vary drastically. And then we come to the dimensionality in terms of defining those nanostructures. It can be 1 dimension, 2 dimension, 3 dimension, or it may not have any dimension along the nanometer length scale. Once it is 3 dimensional, we call it nano quantum dot, or we call them as a nanostructure. Once it is nano dimensionality in 2 direction, we call them nano rods, nano fibers. When it has only one dimension in nano length scale, we call it thin films or lamellae. Once it has no dimension along nano, we call it a bulk structure without any nano entity in it. So, I hope this one comprises the overall overview of nanomaterials and nanostructures, and that is what is the overall aim of this particular lecture. Thank you.